Hi everyone, welcome back to another video from my channel. In our last video, we discussed about two-dimensional vectors or 2D vectors involved in mechanics and solved some example questions from the exam papers. Today we will be learning about the dynamics of a particle moving in a straight line. Before we start our topic though, let us look at some of the models and modeling assumptions that we use for mechanics. These are particle. Dimensions of the object are negligible, meaning the mass of the object is concentrated at a single point and rotational forces and air resistance can be ignored. Rod. All dimensions but one are negligible like a pole or a beam. Mass is concentrated along a line, no thickness, and it is rigid. Light object. The mass of the object is small compared to other masses, like a string or a pulley, meaning we have to treat object as having zero mass, and the tension is the same as both sides of a light string. Inextensible string, a string that does not stretch under load. Acceleration is the same in objects connected by a taut, inextensible string. Smooth surface, a surface on which it can be assumed that there is no friction. We have to assume that there is no friction between the surface and any object on it. Rough surface, a surface on which there is a friction. Objects in contact with the surface experience a frictional force if they're moving or are acted on by a force. Smooth and light pulley. All pulleys you consider will be smooth and light, meaning the pulley has no mass and tension is same on either side of the pulley. And gravity. Force of attraction between all objects. Acceleration due to gravity is noted by g is equal to 9.8 meter per second square. Assume all objects with mass are attracted towards the earth, and acceleration due to earth's gravity is uniform and acts vertically downwards. G is constant and is taken as 9.8 meter per second square. Now let's look at some of the force diagrams. A block of weight W is being pulled to the right by a force P across a rough horizontal plane. Draw a force diagram to show all the forces acting on the block. Here we have the diagram where R is the normal reaction of the rough horizontal plane of the block, P is the force pulling the block, W is the weight of the block, and F is the frictional force or the resistance due to friction between the block and the plane. When the forces acting upon an object are balanced, the object is said to be in equilibrium. Newton's first law of motion states that an object at rest will stay at rest, and that an object moving with constant velocity will continue to move with constant velocity unless an unbalanced force or a resultant force acts on the object. When there is more than one force acting on an object, you can resolve the forces in a certain direction to find the resultant force in that direction. The direction you are resolving in becomes the positive direction. You add forces acting in this direction and subtract forces acting in the opposite direction. In your answer, you can use the letter R together with an arrow, for example R up, to indicate the direction in which you are resolving the forces. In this section, you will only resolve forces that are horizontal or vertical. The resultant force acting on an object will cause the object to accelerate in the same direction as the resultant force. You can also write forces using IJ notation or column vectors as described in my previous video, and you can find the resultant of two or more forces given as vectors by adding the vectors. When a particle is in equilibrium, the resultant force will be 0I plus 0Z. So now let's do an example question. Three forces F1, F2, and F3 are acting on a particle P are given by the vectors F1 is equals to -7, -4, F2 is 4, 2, F3 is AB, where AB are constants. Given that P is in equilibrium, find the value of A and find the value of V. So because for number A, P is in equilibrium, therefore we can say that the addition of all forces, for example F1 plus F2 plus F3 must be 0, as there is no resultant force. So in our last video, we said that a vector can be written as AI plus BJ. And we can also alternatively write that in its column form or column vector form in AB, where this will be the component of I and this will be the component of J. So writing the forces down in its column vectors, we can say that -7, -4, plus F2 which is 4, 2, plus F3 which is AB is equals to the 0 vector, or in its column form 0, 0. So therefore adding we can get that -7 plus 4 plus A, which is the I component, and for the Z component we have -4 plus 2 plus B is equals to 0, 0. So therefore we can say that -7 plus 4 plus A is equals to 0, meaning that A is equals to 3, and we can also say that -4 plus 2 plus B is equals to 0, and so the value of B is 2. In number B, we said that the force F1 is now removed. The resultant of F2 and F3 is R. Therefore, we have to find the magnitude of R. In our last video, we have discussed that if a force F is in the form of AI plus BJ, therefore its magnitude or the modulus of F should be square root of A square plus B square. And so first we have to find R, which is the resultant of F2 and F3. So F2 and F3, which were 4, 2 and A plus B. So because A is 3 and B is 2, we have R being 4 plus 3, which is 7, and 2 plus 2, which is 4. Now we have to find out the magnitude of R, which is the modulus of the vector. So modulus of R is equals to square root of 7 square plus 4 square, which is root of 65, or approximately equals to 8.06 newtons in 3 significant figures. For number 2, we have to find out the angle that R makes with the horizontal. So if we plot the position of R, we can say that if this is I and if this is J, then R must be here, which is 7, and this must be 4, so here, meaning the position of R should be here. And this is a right angle triangle, and so this is 4 and this is 7, and because we have to find the angle with the horizontal, therefore this is our required angle, which is theta. Therefore using tan theta is equals to opposite by adjacent, we have 4 by 7, so theta is equals to tan inverse of 4 by 7, which is 29.7 degrees. Now because we have to find the angle to the nearest degree, therefore the nearest degree should be 30 degrees. So now let's move on to the section of forces and acceleration. A non-zero resultant force that acts on a particle will cause the particle to accelerate in the direction of the resultant force. Newton's second law of motion states that the force needed to accelerate a particle is equal to the product of the mass of the particle and the acceleration produced, which is F is equals to ma, which was also mentioned in our previous video. A force of 1 Newton will accelerate a mass of 1 kg at a rate of 1 meter per second squared. If a force F Newton acts on a particle of mass m kg, causing it to accelerate at a meter per second squared, the equation of motion of the particle is F is equals to ma. Gravity is the force between any object and the earth. The force due to gravity acting on an object is called the weight of the object, and it acts vertically downwards. A body falling freely experiences an acceleration of g is equals to 9.8 meter per second squared, and using the relationship of F is equals to ma, you can write the equation of motion for a body of mass m and weight w newtons, which is w is equals to mg, or its weight. So now let's do an example question. The engine of a van of mass 400 kilograms cuts out when it's moving along a straight horizontal road with speed 16 meters per second. The van comes to rest without the brakes being applied. In a model of the scenario, it is assumed that the van is subject to a resistive force which has a constant magnitude of 200 newtons. So we know that the only resistive force is 200 newtons. Therefore, using the formula of resultant force equals to ma or Newton's second law, we have the resistive force being minus 200 newtons because it's resisting the motion of the car or the van. So we have 400 kg multiplied with acceleration. Therefore, A is equals to minus 200 divided by 400, which is minus 0.5 meter per second squared. The negative sign here represents that the van is decelerating. And so we have to use the equations of motion, which I discussed in our first video of mechanics 1, which was v is equals to u plus at. And so rearranging for t, we have v minus u divided by a. We know that the final velocity v is 0 because the van comes to rest and initial velocity was 16 meters per second. So u is equals to 16 and acceleration is found out to be minus 0.5. So we can substitute those values to get 0 minus 16 whole divided by minus 0.5. So we have 32 seconds. For number B, we have to find out how far the van travels before it stops. So we can use any of the formulas. S equals to ut plus half into at squared. Or we can also use S equals to Vt minus half into at squared. Similarly, we can also use S equals to u plus V whole divided by t multiplied with t. So using this equation, we have S is equals to u, which is 16, plus V, which is 0, whole divided by 2 multiplied with the time, so 32. And this is 256 meters. And for number C, we have to comment on the suitability of the modeling assumption. Now we have assumed that the resistive force is constant, and so realistically this is not possible because the resistive force is unlikely to be constant. So this can be a proper comment. Now let's move on to the motion in 2 dimensions. You can use F is equals to ma to solve problems involving vector forces acting on particles. For example, in our first question we have two forces, 5 newtons and pq newtons act on a particle p of mass m kg. The resultant of the two forces is r. Given that r acts in a direction parallel to the vector 1 minus 2, show that 2p plus q plus 9 is equals to 0. So we know that the resultant of the two vectors must be the addition of the vectors, which is r is equals to 2 5 plus pq. Adding the components, we have 2 plus p and 5 plus q. Because r acts in direction which is parallel to the vector 1 minus 2, as in our previous video we have discussed that if we have two vectors a and b which are parallel to each other, therefore we can say that a is equals to some constant lambda multiplied with b, or it can also be written as a is equals to mu multiplied with b, where lambda and mu are both constants. So here in this case we can say that r being parallel to 1 minus 2, so r is equals to lambda multiplied with 1 minus 2. So we have 2 plus p and 5 plus q is equals to lambda and minus 2 lambda. So we have two equations, 2 plus p is equals to lambda, and we have 5 plus q, which is equals to minus 2 lambda. Which is equation 1 and equation 2. So if we apply equation 1 into 2 plus equation 2, then we should get 4 plus 2p is equals to 2 lambda, so that we can eliminate the lambda and get an equation only in the terms of p and q. So we have 5 plus q is equals to minus 2 lambda, and adding we should get 9 plus 2 plus q is equals to 0, and rearranging in the given form we should get 2p plus q plus 9 is equals to 0. So for number B, given also that p is equals to 1 and p moves with an acceleration of magnitude 15 root 5, therefore we have to find the value of n. So first of all, we have to find the value of q using this equation. So when p is equals to 1, we can say that 2 multiplied with 1 plus q plus 9 is equals to 0. So we have 2 plus q plus 9. Therefore, q plus 11 is equals to 0. Therefore, q is equals to minus 11. So now we have to find out the resultant of the forces. So summation of the F, which is the resultant, we should have 25 newtons plus PQ here, which is 1 and minus 11, and so we should have 3 minus 6. And if you notice, this vector is parallel to the vector 1 minus 2, because if we took a common factor of 3, then we are supposed to get 3 multiplied with 1 minus 2. So now we can find out the magnitude of F, which is square root of 3 squared plus 6 squared, which you're supposed to get root over 45. And so because 45 is 9 into 5, so we can say that 45 is equals to 3 squared into 5, and root over 3 squared is 3. So 3 root 5 is the magnitude of the force. So now using the equation of F is equals to ma, we know that the magnitude of F is 3 root 5 is equals to mass into acceleration, which is 15 root 5. So therefore m is equals to 3 root 5 divided by 15 root 5, and so the root 5 and root 5 cancel each other out, and 3 divided by 15 is 1 by 5 or 0.2, and this is our answer. So now let's move on to the connected particles. If a system involves the motion of more than one particle, the particles may be considered separately. However, if all the parts of the system are moving in the same straight line, then you can treat the whole system as a single particle. You can solve problems involving connected particles by considering the particles separately, or if they are moving in the same straight line as a single particle. Newton's third law of motion states that for every action there is an equal and opposite reaction. So Newton's third law means that when two bodies A and B are in contact, if body A exerts a force on body B, then body B exerts a force on body A that is equal in magnitude and acts in the opposite direction. So now let's do some practice questions. For the first one, we have two boxes A and B of masses 110 kg and 190 kg respectively sit on the floor of a lift of a mass 1700 kg. Box A rests on top of box B The lift is supported by a light inextensible cable and is descending with constant acceleration 1.8 meter per second square. So we have to find out the tension in the cable. So first we have to draw the figure so that we understand the scenario properly. So assuming this is the lift and this is the cable, here there should be tension and there should be box B on the lift as well as box A. So this is the diagram for the forces, where this should be the mass of the box B. So mvg, as we know that weight of any object is equal to mass multiplied with g or mg, and similarly A also has a force of weight being mag, and the lift also has a mass, so it should be 1700 g. So now we have to find out the tension in the cable. So first of all, we need to find out the total mass of the system, and we can consider the whole system to be one single particle of the total mass of ma, which is the mass of A plus mass of B plus the mass of the lift, and whole multiplied with g, because weight is equals to mg, and this being the tension. Because we know that the lift is actually descending with a constant acceleration of 1.8 meter per second square, therefore the resultant force must be downwards. So first let's find the total mass, which is total mass is equals to 110 plus 190 plus 1700, which is 2000 kgs. And so resolving downwards from this diagram, we can say that because the resultant force is downwards given by the acceleration being downwards, we can use the formula F is equals to ma, or the resultant force equals to mass into acceleration, and so we will have the weight, which is 2000 g, subtracted by tension given in a diagram, is equals to mass, which is 2000 again, into acceleration. Now making t the subject, we have 2000 g minus 2000 a, because we know that the acceleration downwards is 1.8, so we have minus 2000 multiplied with 1.8, and using g is equals to 9.8, our value of tension will be 16,000 newtons. And for number 1, to find out the force exerted by box B on box A, we have to draw the diagram again. If this is A and if this is B, then A exerts a downward force on box B, and similarly B also exerts an upward force on box A. So drawing A separately, we have the mass of A, which is 110, and so the weight becomes 110 g, and the upward force of B is our required force, and the acceleration is again downwards. So resolving downwards, we can say that 110 g, or the weight of box A minus force by the box B, is equals to mass of A multiplied with acceleration, which is 1.8 as given. So FB should be 110 g minus 110 multiplied with 1.8, and this is equals to 880 newtons. And we know from this diagram that the force is acting upwards, therefore we can say that FB is acting upwards. So for the second one, we have to find out the force exerted by box B on the floor of the lift. So drawing the diagram again, we can say that this is the lift and this is box B. So box B exerts a force on the lift, and similarly the lift exerts an equal and opposite force on box B using Newton's third law. And we also had the force of A, because A also used to exert a force on box B. So therefore, using B as a particle, we can say that this is the weight, which is 190 G, and additionally we have the force from A, which was the force of B as well because of the Newton's third law. So this is force of A, and this will be the force of the lift. And as usual, the system is accelerating downwards with acceleration 1.8 meter per second squared. So we can resolve downwards again and say that 190 G plus Fa, because both of these forces are acting downwards, so they are considered positive, and Fl being in a negative direction is negative, is equals to mass, which is 190, multiplied with acceleration, which is 1.8. And from the previous diagram, we have seen that because A exerts a force on B, therefore B also exerts an equal and opposite force on A. Therefore, if this is Fb, this is Fa, and Fa, or the force by A, is equals to force by B. So the force of the lift is equals to 190 G plus Fa, which is also Fb, which is 880, minus 190 multiplied with 1.8, and so our final answer is 2400 newtons. For the second one, a car of mass 900 kilograms pulls a trailer of mass 3000 kilograms along a straight horizontal road using a light crowbar which is parallel to the road. The horizontal resistance of the motion of the car and the trailer have magnitudes 200 newtons and 100 newtons respectively. The engine of the car produces a constant horizontal driving force on the car of magnitude 1200 newtons. So we have to show that the acceleration of the car and the trailer is 0.75 meter per second squared for number A. So first we have to draw a diagram of the system, which is something like this. If this is the road, then assuming this is the car, which is pulling a trailer using a rod. So assuming this is the trailer, there should be tension here as well as a tension here, because the car has a resistive force of 200 newtons and the trailer having 100, and the engine has a force of 1200 newtons to the right, or the driving force. So this is 1200 newtons or 1200, and so we have to assume that the whole system is a particle, where this is the net force or the resultant force, which is 1200 acting here, and in the opposite direction we have 100 plus 200 newtons acting. So resolving towards the right, we can say that using F is equals to ma. The resulting force is to the right, so 1200 minus 300, as 100 plus 200 is 300, so is equals to the mass of the whole system, which is 900 plus 300 kg, and whole multiplied with acceleration. So simplifying, we have 900 is equals to 1200 multiplied with acceleration. So A of the acceleration is equals to 900 by 1200, which is 0.75 meter per second square. So for number B, we have to find the magnitude of the tension in the tow bar. So we can consider either of the motion of the car or the trailer. So using the trailer, we have this being T and this is 100. So acceleration is to the right, being 0.75. So therefore, resolving to the right, we can say that tension minus 100 is equals to mass, which is 300 multiplied with acceleration, which is 0.75. So tension is equals to 100 plus 300 multiplied with 0.75, which is equals to 325 newtons. Or using an alternative method, by considering the motion of the car, we can say that this is the tension referring to this portion of the diagram, and this is the driving force is 1200 newton, and this is a resistive force of 200, and the acceleration is in this direction. So resolving to the right, just like before, we can say that 1200 minus 200 minus tension is equal to the mass, which is 900, multiplied with the acceleration, which is 0.75. So the tension should be equals to 1200 minus 200 subtracted with 900 multiplied with 0.75, and so the answer is also 325 newtons. In number C, the car is moving along the road when the driver sees a set of traffic lights being turned red. He reduces the force produced by the engine to 0 and applies the brakes. The brakes produce a force on the car of magnitude F newtons, and the car and trailer decelerate. Given that the resistance to motion are unchanged and the magnitude of the thrust in the tow bar is 100, find the value of F. So for number C, we have to draw the situation again. And so we can say that if this is the trailer and if this is the car, this being the rod, there should be a thrust in both of the vehicles because the deceleration is towards the left, and so we can say that if this is 100 and this is 200 newtons, we have to find out the acceleration to the left. So considering the trailer, we have for trailer resolving to the left, we have tension plus 100 because both of the forces are acting to the left, and drawing a force body for the trailer, we have this being T and this also being 100. and deceleration being to the left. So t plus 100 is equals to the mass, which is 300, multiplied with the acceleration, which is a. Now we know that the thrust is 100 newtons given the question. So we have 100 plus 100 is equals to 300 multiplied with a. And so a is equals to 200 divided by 300, which is 2 by 3 meter per second squared. So now we have to find out the braking force of the car, and considering the motion of the car itself, here we have the force F, and this is the thrust T as illustrated in this diagram. And as usual, this is the resistive force, which is 200, and the acceleration is to the left. Therefore, we can say that resolving to the left again, F plus 200 minus T is equals to the mass, which is 900, multiplied with the acceleration, which is 2 by 3 found here. So F is equals to minus 200 plus T, which is 100 as given, plus 900 into 2 by 3, so our final answer is 500 newtons. So now let's move on to one of the most difficult and complicated parts of the whole topic, which involves pulleys. In this section, you will see how to model systems of connected particles involving pulleys. The problems you answer will assume that particles are connected by a light inextensible string which passes over a smooth pulley. This means that the tension in the string will be the same on both sides of the pulley, and the parts of the string on each side of the pulley will either be horizontal or vertical. More complicated systems will be considered in Chapter 5. You cannot treat a system involving a pulley as a single particle. This is because the particles are moving in different directions. Let's consider this example of a pulley system where there are two masses, capital M and small letter m, and assuming that the capital letter M has a numerical value greater than the small case m. For example, if M was 5 kg and if small letter m was 2 kg, then the pulley system will look something like this, where the acceleration will be this side because the bigger mass will cause the whole system to accelerate and fall to this side, and for the left hand side, the mass, small letter m, will accelerate upwards. So now let's consider the motion of the mass of the capital M. So if this is M, then this will be capital Mg, and upwards will be tension acting, and the acceleration will be downwards because M is greater than the small letter m. So this is A. So therefore, resolving downwards, we can say that Mg minus tension will be equals to Ma because of the equation F is equals to Ma, or the resultant force, which is downwards, is equals to mass of the particle multiplied with the acceleration. Now considering the motion of the small letter m, we can see that this is mg or small case mg, and this is tension, and because the acceleration is upwards this time from this portion, we can say that tension minus mg or the small case mg is equals to ma, which is mass multiplied with acceleration, and we can solve these two equations simultaneously to get either acceleration or tension in terms of m or n. So now let's look at some questions from exercises. For example, here we have exercise 4F, and number 2, we have a pulley system given that two particles P and Q have masses km and 3m respectively, where k is less than 3. That means the whole system will accelerate downwards in this position, and the left side will accelerate upwards. The particles are connected by a light inextensible string which passes over a smooth light fixed pulley. The system is held at rest with the string taut, the hanging parts of the string vertical, and with P and Q at the same height above a horizontal plane as shown in a diagram. The system is released from rest. After release, Q descends with acceleration 1/3 g. So now we have to calculate the tension in the string as Q descends. So if we redraw the pulley, if this is P with Km mass, so this should be Kmg, and this being Q should be 3mg. Here there should be a tension as well as here. Similarly here we should have a tension and a tension here as well. So because we know that Q descends with an acceleration of 1/3 g, so we can say for Q resolving downwards, we can say that 3mg, or the weight of Q minus tension, is equals to 3m multiplied with a, which is acceleration. So the tension rearranging should be 3mg subtracted with 3ma. Now because a is 1/3, therefore we can say 3m multiplied with 1/3 of g. So this simplifies to 3mg subtracted with mg, which is also 2mg newtons. For number B, we have to show that k is equals to 1.5. So we have to consider the motion of P. So for P, drawing the diagram again, this is tension and this is kmg. Acceleration is upwards because on the left side the particle accelerates upwards and on the right side the particle accelerates downwards. So this is 1/3 g, and resolving vertically upwards, we can say that tension subtracted with kmg is equals to km multiplied with acceleration, which is following the formula of resultant force F is equals to ma. So therefore tension being 2mg, we can write that being 2mg subtracted with kmg is equals to kma, which is 1/3 of g, 1/3 of g. So multiplying both sides with 3, we get 6mg minus 3kmg is equals to kmg. So therefore, making k the subject, we get 6mg is equals to 4kmg. And so simplifying, we can say that k is equals to 6mg whole divided by 4mg, and this is 1.5. So for number C, we have to state how we use the information that the pulley is smooth. Now if you refer to the modeling assumptions that we covered previously, we had a smooth and light pulley being a pulley has no mass and the tension is the same on either side of the pulley. So for number C, we can say that the tension along both sides of the pulley should be same. And this is our modeling assumption. And this is how we use the information that the pulley is smooth. For number D, we are said that after descending for 1.8 seconds, the particle Q reaches the plane. It is immediately brought to rest by the impact with the plane. The initial distance between P and the pulley is such that in the subsequent motion, P does not reach the pulley. So we have to show that the greatest height reached by the particle P is 1.26 g above the plane. So using the information given, They said that Q descends for 1.8 seconds. It is brought to rest, and it was initially at rest. Therefore, we can say that U is equal to 0. We know that the acceleration is 1/3 of G. Therefore, we can use the equation S is equals to ut plus half into at square to calculate the distance traveled or the displacement. So initial velocity is 0 multiplied with 1.8 plus half into acceleration, which is 1/3 g, multiplied with time squared, which is 1.8 squared, and this is equals to 0.54 g meters. And now we have to consider the motion after Q reaches the plane. So initially both of the particles were at the same height, so this should be 0.54 g, and so as soon as Q falls to the ground, we can say that if Q moved a distance of 0.54 g, therefore the particle P should also move the same distance because Q was the particle that pulled P along with it. So therefore we have to consider the motion when the tension is 0. So we can find out the velocity of P as soon as the wire or string becomes slack. So using the formula, initial velocity is 0 plus A, which is 1/3 of G, multiplied with time, which is 1.8, and therefore the final velocity must be 0.6 g meter per second. So this is the final velocity of particle P as soon as the string becomes slack. So after it becomes slack, we can say that the particle P starts moving under free fall, and if the upward is positive, therefore G must be negative. So as we know, in a vertical motion, the maximum height reached by the particle is S, and at the maximum height, the velocity or the final velocity of the particle is 0, because initial velocity was calculated as 0.6 g. Therefore, we can use the formula v square is equals to u square plus 2as. So rearranging for s, we have v square minus u square whole divided by 2a, because the final velocity here is 0 squared and u squared is 0.6 g whole squared, and whole divided by 2 multiplied with acceleration, which is minus g here. Our answer is 0.18 g meters. So considering the full motion of particle P, initially it was 0.54 g meters above the ground, and after Q also moved a distance of 0.54 meters, it also moved the same distance of 0.54 meters g, and as soon as Q stopped, we can say that the particle P was starting to move under free fall, so therefore minus g becomes the acceleration, and we have calculated that the distance traveled in that motion is 0.18 g. So the total distance traveled will be the sum of all three distances, which is 0.54 plus 0.54 plus 0.18 and whole multiplied with g, because they were multiplied with g initially, which we get being 1.26 g, and this is our answer. For number 3, we have two particles A and B with masses m kg and 3 kg respectively, where m is greater than 2. So therefore we can say that the acceleration to the left side is downwards and the acceleration of the right side is upwards, because m is greater than 3. Therefore A is the particle that causes the pulley to accelerate downwards. So initially A is 2.5 meters above horizontal ground. So for number A, we know that the distance traveled is 2.5 and the time taken is 1.25 seconds, and the initial velocity of both were 0. So we can use the equation s is equals to ut plus half into ac squared, and this will be 0 because initial velocity is 0, and plus half into a multiplied by t squared, which is 1.25 squared, and s is 2.5. So therefore acceleration is equals to 2.5 divided by half into 1.25 squared, which we get being 3.2 meter per second squared. And this is our answer for A. For number B, we have to find out the tension in the string as A descends. So considering the particle A, this should be mg, and this should be tension T. And here we have the acceleration, which is downwards, being 3.2. But because we don't know the numerical value of m, therefore we cannot use the system A. Rather, we have to use the system B because we know the mass of B, which is 3 kgs. So its weight must be 3g, and the tension will be upwards as being T. So because we know that the acceleration of B is upwards because m is greater than 3, so this is 3.2 upwards, and for B resolving upwards, we can say that tension minus 3g is equals to mass into acceleration, which is 3 into 3.2. So tension rearranging becomes 3g plus 3 multiplied with 3.2, and this should be 39 newtons. For number C, we have to show that m is equals to 65 by 11. So now we can use the system for A, which is where we resolve downwards because the acceleration is downwards. So we can say that mg minus tension is equals to ma. Using Newton's second law, F is equals to ma. So making m the subject, we can say that mg minus ma is equal to tension. And taking a common factor of m, we get m multiplied with g minus a is equal to t. And so m must be t divided by g minus a. And because tension is 39 divided by g, which is 9.8, subtracted with acceleration, which is 3.2. Plugging the values, we should get 39 by 6.6, which is 65 by 11. And for D, we have to state how we use the information that the string is inextensible. So referring back to our modeling examples, so referring back to our modeling assumptions, we can say that inextensible means that acceleration for both A and B is same in value. And for number E, we have to say that, and for number E, when A strikes the ground, it does not rebound and the string becomes slack. Particle B then moves freely under gravity without reaching the pulley until the string becomes taut again. Find the time between the instant when A reaches the ground. Find the time between the instant when A strikes the ground and the instant when the string becomes taut again. So for A, drawing the pulley again, when A moves a distance of 2.5, we can also say that they also move a distance of 2.5 meters. And similarly, just like before, we have to calculate the time between which B started to reach the maximum height. So first, we have to find out the velocity of B as soon as the string becomes slack, which is the final velocity of the motion when acceleration was 3.2. So we don't know V, but we know that initially it was 0 and acceleration is 3.2, and the time taken was 1.25 seconds as given in the question. So therefore, we can use the equation v is equals to u plus at to find out the final velocity of B just as soon as the string becomes slack. So u is 0, a is 3.2 multiplied with t, which is 1.25, and we get 4 meter per second. So now considering the motion of B starts moving under free fall because the string is slack. And therefore the motion looks something like this. And we know the initial velocity is 4 because this is the speed at which the string becomes slack, and the acceleration is g again, which is negative because we are considering the initial velocity, which is upwards, being positive. Therefore we can consider the total time taken, which is t, and as we know the vertical motion is parabolic. Therefore we can say that it's symmetrical, meaning if the velocity is 4 here, therefore the velocity here should be minus 4 because of the opposite direction. So using the equation v is equals to u plus at, velocity is minus 4 and initial velocity is 4 plus acceleration, which is minus g, multiplied with t. So we can calculate the time being minus 4 whole divided by minus g, which is 8 by g seconds. Or using fractions, we can say that 40 by 49 seconds is the time. So now let's move on to number 5, where it's given that a box P of mass 2.5 kg rests on a rough horizontal table and is attached to one end of a light inextensible string. The string passes over a small smooth pulley fixed at the edge of the table. The other end of the string is attached to a sphere Q of mass 1.5 kg, which hangs freely below the pulley. The magnitude of the frictional force between P and the table is k newtons. The system is released from rest with the string taut. After release, Q descends a distance of 0.8 meters in 0.75 seconds. So modeling P and Q as particles, for number A1, you have to calculate the acceleration of Q. So because we know that S is equals to 0.8, time is equals to 0.75, and we know that initially it was at rest, so u is 0, and so we have to find out the acceleration, and using the equation S is equals to ut plus half into h square, we can make a the subject and we should get 2s divided by t squared because u is 0, so 2 into 0.8 divided by t square, which is 0.75 whole square, and the value of acceleration is 128 divided by 45, or to 3 SF or significant figures, we have 2.84 meter per second square. So for number 2, we have to show that the tension in the string is 10.4 to 3 SF. So we have to draw the diagram to understand. If this is the pulley, then this is tension and this is also tension. and if this is q, then this is its weight, which is 1.5 g, and the acceleration will be downwards because q is the one that pulls the pull system down. So therefore we can say that for q only, resolving downwards, mg, or its weight 1.5 g minus tension is equals to ma, which is mass into acceleration. So 1.5 multiplied with 2.84. Rearranging for t, we get t is equals to 1.5 minus 1.5 multiplied with 2.84. And so the value of tension is 10.44, or approximately 10.4 newtons, which is in 3 significant figures. And in number 3, we have to find the value of k. So we know that the frictional force for this surface, because it's rough, therefore it must be k, and drawing the particle of P, we have tension here, and we have the force friction, which is k, and vertically we have mg, which is the weight, and upwards we have the normal reaction force. But here we only have to work with tension and k because the acceleration is towards the right. So therefore, resolving horizontally to the right, we can say that tension minus k is equals to ma, which is 2.5 into acceleration. And so rearranging for k, we have t minus 2.5 a, and tension was 10.44 minus 2.5 multiplied with acceleration, which is 2.84, and so the value of k is approximately 3.34 newtons. And so in number B, we have to state how in our calculations the information has been used that the string is inextensible. Referring back to our modeling assumptions, we know that inextensible means that the acceleration is the same for both objects. So meaning acceleration, or A, is same for both P and Q. And now let's move on to our final math, which is from the chapter review 4, which is of number 15. And we are given that two particles P and Q have masses 0.5 kg and 0.4 kg respectively. The particles are attached to the ends of a light inextensible string. The string passes over a small smooth pulley which is fixed above a horizontal floor. Both particles are held with the string taut at a height of 2 meters above the floor as shown. The particles are released from rest, and in the subsequent motion, Q does not reach the pulley. Write down an equation for motion of P. So in A1, first we have to say that because P has a greater mass, therefore the acceleration will be downwards for the left side and the acceleration will be upwards for the right hand side, because the overall force of the weight of P, which is 0.5 g, is more dominant than 0.4 g. So here will be the force and this will be the tensions. And so we have to find out an equation of motion for P. So if this is P, this is 0.5 g, and this is the tension T for P. And because the acceleration will be downwards as explained previously, so therefore resolving downwards for P, we can say that 0.5 g, or its weight, subtracted with T, is equals to mass into acceleration, which is 0.5 into A, and this is equation 1. For number 2, we have to write an equation of motion for Q. So if this is Q, this is its weight, which is 0.4 g, and similarly this is the tension. And because we know that on the left hand side P accelerates downwards, so therefore Q must accelerate upwards. So acceleration is upwards, and so resolving upwards for Q, we have tension minus 0.4 G is equals to 0.4 multiplied with A, following the equation of resultant force equals to ma, which is Newton's second law. So for number B, we have to find out the tension in the string immediately after the particles are released. So from both our equations, we have to solve them simultaneously, and to get the tension, we have to eliminate the acceleration or the A variable in these two equations. So we can say applying equation 2 divided by 1, we can say that T minus 0.4 G is equals to 0.4 A, and whole divided by 0.5 G minus T, and on the right hand side we have divided by 0.5 A. So you can see that the A terms cancel each other out, and we have T minus 0.4 G and divided by 0.5 G minus T is equals to 4 by 5. So therefore, multiplying both sides with 5 by 4, and therefore by cross multiplying we get 5T minus 2G is equals to 4 into 0.5, which is also 2G minus 4T. And so further simplifying, we can say that 5T plus 4T is equals to 2G plus 2G. Therefore 90 is equals to 4G, and so our value for tension is 4G by 9, which is approximately equals to 4.36 newtons. So for number C, we have to find out the acceleration. So either from equation 1 or 2, we can say from equation 2, T minus 0.4 G is also 4 by 9 G subtracted with 0.4 G is equals to 0.4 A, just substituting the value of T. Therefore, acceleration is equals to 4 by 9 G minus 0.4 G whole divided by 0.4, and so the acceleration is equals to 1 by 9 G meter per second squared. And this is our answer. So for number D, it said that when the particles have been moving for 0.2 seconds, the string breaks. So find out the further time that elapses until Q hits the floor. So in order to solve this, first we have to consider the motion of P and Q. And because we know that the particles have been moving for 0.2 seconds, therefore the acceleration that we found previously, which was A is equals to 1 by 9 G meter per second squared, is the acceleration that applies for 0.2 seconds. So we can say that during 0.2 seconds, the particle Q moves at a certain distance s1 for T is equals to 0.2 seconds, and using the acceleration of 1 by 9 G meter per second squared. And so we can find out the velocity, and so we can find out the final velocity v at which Q was moving after the string broke. So therefore, using the equation, v is equals to u plus at. U is 0 because initially Q was at rest, plus a, which was 1 by 9 G multiplied with t, which is 0.2, and so we get 1 by 45 G meter per second. And we also find out the displacement S1, which is found using S is equals to ut plus half into at squared. So u is 0, so this is 0, plus half into acceleration, which is 1 by 9 g multiplied with t squared, which is 0.2 squared. And so the value of S1 is 1 by 450 g meters. So if you consider the full motion of Q, which is something like this, initially it was at this point along with P, which is 2 meters from the ground, and after the string broke, it traveled a distance of 1 by 450 g meters as found out from here, and this is the max height, and then it promptly fell through a displacement of 2 plus 1 by 450 g. So if you consider this point being the reference point or displacement equals to 0, so therefore if the particle falls through a distance of 2 plus 1 by 450 g, therefore we can say that the displacement is negative of 2 plus 1 by 450 g. So we can express that being S is equals to ut plus half into at squared. And at this point we can say that the initial velocity was 1 by 45 g, because this was the point at which the string broke, so therefore this is the velocity or the initial velocity. So therefore using that equation we can say that the displacement from this reference point to the ground is minus 2 plus 1 by 450 g. So minus 2 plus 1 by 450 g is equals to ut, which is 1 by 45 g t plus half into at squared, and as usual the acceleration is minus g because it's in free fall. So rearranging we get half into gt squared minus 1 by 45 g t minus 2 plus 1 by 450 g is equals to 0. So using the equation, if we had ax squared plus bx plus c is equals to 0, therefore the solutions are x is equals to minus b plus minus root over b squared minus 4ac whole divided by 2a. So therefore using that equation we can say that 1 by 45g plus minus root of 1 by 45g whole squared, because this is b in our equation, minus 4 multiplied with half g multiplied with c, which is minus of 2 plus 1 by 450 g, and so whole divided by 2 into a, which is half g, and using the calculator we can get the values of 0.665 seconds or minus 0.621 seconds. Now because we know that time is always positive, therefore t is equals to 0.665 seconds, and this is our final answer. So thank you all for watching. Please give a like, comment, share and subscribe if you enjoyed this video. See you later in our next video. Goodbye.